Hey, this lab is on optics, and in particular, we're going to talk about lenses. Okay, we're going to talk about ray diagrams and a couple other things. Also, this lab is kind of a good review for mathematics. Okay, you'll see what I'm talking about in a little bit. All right. Um, we're going to talk about, as I said, lenses. Okay, the things that you find on microscopes and telescopes and your eyeglasses and your contact lenses. Okay, there's going to be two types. Okay, the first we'll talk about is called converging. To converge means to come together. So in converging lenses, the rays of light are going to come together. So this is converging, a converging lens. Okay, and it's also known as a positive lens. Okay, so this is a synonym. A positive lens is also a converging lens. And one other synonym for converging and positive is convex. Okay, convex. Okay, so all these words are synonymous: converging, positive lens, or convex lens. Okay, the other type of lens we'll be talking about is called diverging. Right, to diverge means to go apart. We'll talk about this diverging. So we have a diverging lens. Well, obviously, it's going to be called a negative lens. If a converging lens is positive, this will be a negative lens. Okay. And a third synonym is going to be concave because it's going to be shaped concave, like a cave going inward. You'll see what I'm talking about in a bit. Okay. All right. So we'll do the particulars on that in a bit. Okay. The next thing I'm going to talk about, and this will be on the quiz. This picture that I'm going to draw is going to be on the quiz. Okay. So we're going to talk about a ray diagram. Okay. And exactly, well, hopefully neater than I'm going to draw, but I'm going to ask this exact thing on the quiz. So try to learn it and give it to me exactly as I try to draw it. As I said, hopefully a little clearer, okay? We're going to do a ray diagram for a converging lens. Okay, so I'm going to label my picture. And as I said, I'm going to try to be as neat as I can, but no guarantees here on Zoom. Okay, first I'm going to draw a line right down the middle. So I'm going all the way down, right? It's supposed to be a straight line, okay? A straight line. I'm going to keep going. All right, that's good enough. And this is going to be called the optic or optical axis. Goes right through the middle, optical axis. Okay, there's one labeling. Okay, now I'm going to put my lens. This is going to be my converging lens. Okay, and it's supposed to be symmetric, supposed to look beautiful. Okay, that's a beautiful lens. All right, it's not so beautiful, but that's okay. Okay, you see the way it curves outward. Okay, and that's convex. Okay, and it's supposed to pass. This is supposed to the optic axis is supposed to pass right through the middle. Okay, let me see. Do I have an eraser? Yeah, I have an eraser. So let me try to fix this. Okay, so let's go down a little. Let me fix this if I can a little better. All right, that's a little better. Okay, so as I said, the optic axis is supposed to go right through the middle of this lens. Okay, now I'm going to draw an arrow going up. Okay, I'll make this a little dark. Doesn't matter. Okay, and it's going up. Okay. And this is going to be our object. So I'm going to say it's an upright because the arrow is pointing up, upright object. Okay. That's our object. Now we're going to draw three rays. So we're going to do three rays in this ray diagram. Okay. And as I said, try to follow what I'm doing, even though it's not going to be so neat. All right. I'm going to take the first ray is going to go parallel to the optic axis. So I'm going to go parallel, straight, as straight as I can do. Okay, straight, and it's going to hit the lens, okay? I'll make a little arrow there. I'll call this 1. Doesn't matter. Doesn't matter. You don't have to put the 1 or anything like this. So if I can get my pen to work. Okay, come on, pen. Let's get this going here again. Looks like a smile. Okay. All right, that's 1. This is going to be ray 1. It doesn't matter. As I said, when it hits the converging lens, what it's going to do is going to converge towards the optic axis. So I'm going to try to draw a straight line as straight as I can. Okay, and then it's going to go forever. Okay, and again, it doesn't matter. I call this ray number 1. Okay, now I'm going to take a second ray, and it's going to go from the top of the arrow, and it's going to pass through the lens. And again, I'm going to try to do this as neatly as I can, and it's going to pass right through the middle. It's supposed to be the middle of the lens. Okay, it's going to keep going, keep going, keep going like that. Okay, I'll call that ray 2. Okay, this is ray 2. Again, it doesn't matter what I call 1 or 2. These are just silly numbers. Okay, and then the third one is going to come here, cross the optic. Oopsie, go straight. Oopsie, go straight, cross. Oops, oh, supposed to come here. Okay, and this is pretty bad. Okay, hit this lens and then come out straight. Okay, now if I did this correctly, all these lines are supposed to meet at this one point. Okay, okay, and this would be ray number 3. Okay, I'll put a little 3 there. Once again, it doesn't matter what I call 1, 2, or 3. Okay. The point here where it hits the optic axis, we're going to call it capital F. Okay, and capital F, I'll write it up here. Capital F is called the focal point of the lens. Okay. Now, if you look on this side of the lens, the ray number 1 also crosses the optic axis, and it turns out this is also F. Okay, so it should be the same distance from the lens on both sides. Again, if I drew this neat, so we're going to call the distance from the focal point to the lens. This distance we're going to call this little f. Okay, and I'm going to draw an arrow to the lens and to the focal point. Okay, and again, this to here is also little f. Okay, it's supposed to be the same distance on both sides. I'll talk about the symmetry in 1 second. Okay, little f is called the focal length. Length. The focal length is the distance. Oh, I put a T in it. It's no T. The focal length is the distance from the focal point to the center of the lens. Okay. Now, here's the object. Let's look at the object. I'm going to draw a dotted line down here. Right? And then from the middle of the lens, I'll draw a dotted line here. The distance from the lens, the center of the lens, to the object, we're going to call d sub O. Okay? And that's going to be this distance. D sub O, the O stands for object. So this is going to be the object distance, okay? So d sub O is the object distance, the distance of the object, in this case, our upright object, to the lens, object distance. Okay? And then here, we look where all these lines, all these rays converge. This is where our image is. So I'm going to draw an arrow going like this. Okay, you see the arrow is pointing down, and this is our image. So this is where our inverted image, see, it's inverted, the arrow is. So if you look through a lens, you'll see things upside down, just like our eyes actually see things upside down, and it's our brain that inverts things, right? Inverted image. So this is where the image is. Okay, I'm going to take a dotted line here. And the distance from the lens to the image is called d sub I for image distance, okay? So this is how I want you to label the diagram if I give this on a quiz. Okay, so d sub I, I'll write that here, d sub I is called the image distance. Okay, so we have object distance, image distance, and focal length. All right, and when we have an object on one side, they will converge to make an inverted image on the other side of the lens. Okay, and the rays cross the optic axis at a point called the focal point. And if we look at what I called ray number 1, ray number 2, ray number 3, well, ray number 1 and ray number 3 are actually the opposites. You see, if the image was our object, right, then the line, right, ray 3 goes parallel and then crosses on the other side through the focal point. Well, ray 1 goes parallel and on the other side of the lens crosses the optical axis through the focal point. So ray 1 and ray 3 are actually mirror images of each other, while ray 2 goes right through the center of the lens, okay? Now, the image distance, di, the object distance, do, and the focal length, f, are all related by a single equation. Very simple equation. This equation is called the lens maker's equation. Lens. So this is what they use at all the optic stores to make your lenses. Lens maker's equation. The equation, okay? And it's a simple equation, but students have a lot of trouble with it because they cannot do fractions, okay? So I'm going to give you the image maker's equation that relates di, do, and f, okay? So let's give it, and then we'll talk about it. And here it is, very easy. 1 over f, 1 over the focal length, is equal to 1 over the object distance plus 1 over the image distance, okay? And this is our wonderful equation for the whole lab, okay? And it looks very simple. Okay, so for example, let's do a quick example. Suppose I tell you the focal length of a lens, I'm going to say is 2 centimeters. Okay, and let's just say that the object distance, we place an object 6 centimeters away. Okay, and then I ask you, where is the object? Where is the image? Where is the image formed? Is the image formed? Okay, that's an O formed. Okay, in other words, we want to find d sub I. Okay, well, we go to our lens maker's equation, 1 over f, excuse me, 1 over f is equal to 1 over do plus 1 over di. Okay, well, we know f is 2, so we have 1 over 2 equals, well, the object distance is 6, so we have 1 over 6 plus 1 over di. So now we have to solve for di, okay? So let's go over here. We have 1 over di is equal to 1 over 2 minus 1 over 6. Okay, so how do we solve this? How do we do this? Well, we need the common denominator. Common Common denominator, right? Well, this problem looks pretty easy, right? The common denominator is 6. So 1/2 is 3/6. Now we subtract 1/6, and that's equal to 2/6. So this equation tells me, pay attention, Now watch out, because here's where students make a mistake. 1 over di, 1 over di is equal to 2 divided by 6. So if we flip this equation, we got to flip it, because I don't care what 1 over di is. I care about di. So if I flip it, I get di is equal to 6 divided by 2. And that should be 3. And of course, we're using centimeters, so the answer would be 3 centimeters. Okay, so there's a simple example. Now let me tell you about the hard part of this equation, okay? And then we'll get to the lab, a couple things about lab. And I'll give you the diagram for a diverging lens. All right, so let's go over this. Okay, so we have 1 over f equals 1 over do plus 1 over di. Okay, so first thing we want to remember, and this is the most important thing almost of the entire lab, is that the focal length f is a constant. In other words, if you're wearing a pair of glasses and the focal length is 20 centimeters, I'm just making this up. If that's the focal length of your lens, then no matter where the object is or where the image is formed, the focal length will always be 20 centimeters. That's the way the lens is made. So the focal length is a constant, doesn't change. Okay, so let me show you a simple example. Suppose I have this. Suppose DO is 30 centimeters. I don't care. Okay, and suppose DI is 50 centimeters. Then 1 over F equals 1 over 30, 1 over DO, plus 1 over 50. Okay, and we can calculate what the focal length is, right? We could just do this math. Okay, we can find the common denominator, which is what, 150, and we can do, okay, so we can do it. And then don't forget to flip it. But I want you to notice that whatever this number is, all right, look, so let's see. So this would be 3 over 150 plus 5, I'm sorry, 5 over 150, excuse me, plus 3 over 150. So this is equal to 8 divided by 150. And so the focal length, don't forget to flip. The focal length is equal to 150 over 8. Okay? Notice now that if DO was equal to 50 centimeters and DI was equal to 30 centimeters, we get the same result, don't we? 1 over F equals then 1 over 50 plus 1 over 30. And it's the same exact equation. I just mixed 1 over 50 and 1 over 30, but it's the same equation. And when we flip, we find F again is 150 over 80, as it should be. Over 8, sorry. Okay, and I don't care what that number is right now. Okay, so for any 2 points, 30 and 50, there would be another point, F 50 and 30, that give you the same focal length. So there'll always be pairs of numbers that give the same focal length. So if DO was 17 and DI was 50, then I can have DI is 17 and DO is 50. Again, you just flip-flop them, so you get the same result. Okay, so keep that in mind. All right, now let's talk about the hard part of this equation. Before I do that, let's do some math. Okay, very simple math. So suppose I have 1 over 1. Okay, now suppose I take 1 over 10. Well, we know 1 over 10 is smaller than 1 over 1. What if I take 1 over 100? Well, that's even smaller. And what if I take 1 over 1,000? That's even smaller. And what if I take 1 over 1,000,000? That's even smaller, right? Right? This is equal to 1. This is equal to 0.1. This is equal to 0.01. This is equal to 0.001, etc., right? So as the denominator gets bigger, as the denominator gets bigger, or approaches infinity, right? There's really no infinity, but gets it. Oops, that's supposed to be infinity. Infinity, right? Then the fraction approaches 0, right? This is getting smaller and smaller, right? From here to here is smaller and smaller. 1 over 10 million is even smaller. 1 over a billion is even smaller. 1 over a trillion, zillion, kabillion is even smaller. So as the denominator gets bigger, the fraction approaches 0. Okay, so what does that mean? Suppose, now listen to my words, suppose we place our object at infinity. Place our object at, I'll put in quotes, infinity. Well, that just means very far away, okay? Very far away. Okay, what that means is that DO is very, very big, very, very big. Okay, well, what happens to our equation? Well, we have, again, same equation. 1 over F, lens maker, equals 1 over DO plus 1 over DI. Okay, now what did we just say? We said this thing, DO, is getting very big, approaching infinity. So if the denominator gets very big, then this thing is 0, goes to 0. And if that goes to 0, then we have, all we're left with is 1 over F equals 1 over DI. Or then the image would be formed at the focal point, at the focal length, right? It's the focal point, but at the focal length. The value would be the focal length, right? So if 1 over F is equal to 1 over DI, that means DI is just equal to F. The image is formed at the focal length. Okay? Very good. Keep that in mind. All right. In the lab write-up, what they want to do is they want to get the focal length of a lens. Oopsie, we want to get the focal length of a lens. Now, if you're in lab and you want to get the focal length of this lens, one thing you can do is you can put the object far away. Far away. Now, how far away? Well, if it's 1 meter away, just say it's 1 meter. Remember, 1 meter is 100 centimeters, right? So if we take 1 over DO is equal to 1 over 100, well, 1 over 100, right, is 0.01, right? That's equal to 0.01. And that's very small. So if we say this is very small, right, 100, right, 1 over 100, very small, that it's almost 0. Okay, so if we can put an object a meter away, then we can take the 1 over DO to be about equal to 0. And that would mean DI, where the image is formed, is equal to the focal length. Okay, now how do we do this? How do we do this? Well, in the lab, we're in lab, the lights that are above are fluorescent lights. Now I'm going to draw these like this. There's usually like 3 bulbs together, something like this. 3 bulbs together. Okay. Now here's the table. Here's a table, and there you are. Oops, the table's bigger than you. All right. What you're going to do is you're going to hold up the lens. All right. And these lights will actually, on a piece of paper, you will get to see, if you move the lens, you'll see the 3 lines of the 3 lenses, of the 3 bulbs. So you move your lens up and down until you just focus where you can see the 3 lines of the light. When you do that, this light would be our object. Okay? And this distance is about a meter, right? So we can take DO, 1 over DO, to be approximately equal to 0, because 1 over 100, remember we said 1 over 100, is about 0. We take it to be very small. Then we can measure, I'm sorry, my picture's so terrible, the distance from the lens to where those lines are, okay? So if the lines are on a piece of paper here, these are the lines on a piece of paper, right? And you're holding, this is your hand holding, right, holding this lens. And the light is somewhere up here. Then the distance from your lens to those clear lines on the piece of paper on the desk, this would be d sub I. So if we take a ruler and we measure, we got to hold this as steady as we can, as long as we have a clear image, right? So we want this to be a clear lines. We want it to be as clear as possible. You'll see as you move the lens, it'll get a little blurry, but if you kind of hold it still at a position, you can see you can get those lines pretty clear. Try to hold it, and your lab partner can then take a ruler and measure DI. If you measure DI, remember, we have 1 over F equals 1 over DO plus 1 over DI, right? Now, if this is 0, almost 0, right? It's 1 over 100. So we're going to take this to be almost 0. Then we have that the image distance we're measuring with our ruler is approximately equal to the focal length. So there's our first measurement of the focal length. Okay? Hope that helps. All right. Now, here's the next thing we're going to do. In lab, we're going to have an optic table. Okay? And I'll try to draw this, okay? And so we're going to have an optic bench. And here there's going to be an object. What the heck is the object? The object, it turns out, is a light. And carved out is an arrow. Okay? Carved out is an arrow. And the light is going to project that light going like this, okay? Now on this bench, okay, we're going to put our lens, and we want to move this. We want to move this. Because this thing then, we want to make an image, and here we have a screen. Okay? And what's going to happen when we move this, wherever we move it, eventually on the screen, we're going to see, remember, an inverted image. We're going to see the arrow here, inverted image, inverted image. Okay? So the distance from this object to the screen, this would be DO. Okay? So suppose this is at 0. And suppose this thing, I'm making this up, is at 60 centimeters. Okay? So we know DO is equal to 60 centimeters. Now, we have to measure the distance from the screen, from the lens to the screen, not from the light to the screen, from the lens to the screen. And this will be the image distance. So on this optic bench, if we started at 0 and that was at 60, and then we notice, ooh, this thing now, the screen is at 90 centimeters. Well, the image distance is not 90, because if this is 90 and the lens is 60, then the image distance is 90 minus 60 would be 30 centimeters. Okay. And so we can figure out the focal length, right? Because 1 over f equals then 1 over do. And I'm making these numbers up, plus 1 over di. So it would be equal to 1 over 60 plus 1 over 30. And again, we can get those numbers, and I'm not going to work it out. Now, notice we also would have an image formed, right? Remember, the focal length doesn't change. This is a constant. Well, since DO was 60 and DI was 30, well, you should get the same result if we do 1 over 30. That would be 1 over DO plus 1 over 60. Right? So if we put this lens at 30, let's say this is 30. If this was at 30 from, from the object to the lens, if that was 30, then the image would be at 60. You see? So you get 30 and 60, 30 for DO, and DI equals 60. You get the same result for the focal length as if DO is 60 centimeters and DI was 30. Okay, so we get a pair of points, right? 30 and 60 and 60 and 30. Okay, all right. And so we're going to move the screen in lab at a bunch of places, move the lens, if we move the screen, then we have to move the lens and see where we have to move it to get our two images. Okay, so there'll be two sets of points. So for every image, or position of the screen, we're going to have two sets of points. Okay, two sets of points. So in the case we just did, what do we have? We had 30 and 60 were one set, and the other was 60 and 30. Sorry, I'm writing too small. Okay, 30 and 60. Okay. All right, so how are we going to use this? Well, what we're going to do is we're going to do a graph. And suppose I had DO was 60. Just say DO was equal to 60 centimeters. Well, what is 1 over DO? Well, 1 over DO is equal to 1 over 60. And 1 over 60, if I put it in my calculator, 1 divided by 60 is equal to 0.016 equals, or 0.0166666, so I'll put 0.17. Okay? If DI is equal to 30 centimeters, then 1 over DI would be 1 over 30. And let's see, so 1 divided by 30 is equal to 0.033, right? 0.033. Okay, now what we're going to do is we're going to graph this stuff. Okay, we're going to graph this stuff. And I think in lab, they've already made the markings for you. Okay, so I'm just going to do something like this. Okay, it doesn't matter which axis is which. If I put this as 1 over DO, and this axis is going to be 1 over di. Okay, so we just said 1 over do is 0.017. Okay, so suppose this is 0.0 1, all right, and here is 0.015, and here is 0.02, whatever, okay? And again, I'll do something like this. 0.01, 0.02. I'm just doing this quickly, so forgive me. 0.03. All right. 0.04. All right. So let's see. So we need 1 over do is 0.17. So here's 0.15, here's 0.16, here's 0.17. I don't know, so somewhere around here. Okay. And di, 1 over di is 0.033. So here's 0.03, 0.04. So it's going to be somewhere here. So if I go up, something like this, I'm going to get a point over there. Okay. Now, remember, we said I can also have 1 over do equals 1 over 30. And 1 over di equals 1 over 60. Okay, so now 1 over do is 0.033. So now 0.033, right? So here's 0.03. So 0.033, I don't know, is somewhere over here. And 1 over 60 is 0.017. So that's somewhere up like this up here. So the other point will be something like this. Okay, something like that. Okay, so each time I get an image, I can plot 1 over do and 1 over di, and then I can flip the numbers 1 over di and 1 over do and get 2 sets of points. All right, now if I do this for a couple of places for my screen, we're going to get different points. We're going to get that. And what we should get is a straight line, right? We should get a straight line, but we won't because our numbers are off. So what we're going to do when we do all these sets of points, we get 2 and 2, 2, is eventually we're going to try to draw a straight line through all of these. That's supposed to be a straight line through all the points as well as I can, okay? This is our goal, is to draw this straight line. Now, what does this straight line mean? Well, let's look. Let's look at this point right down here. So let's say where this hits the axis. If I can measure where this hits the axis, well, what's going on there? Well, at this point, it's on this line, this horizontal line. Here, the value of 1 over do at this point, 1 over do equals 0, right? Because there is no 1 over do. Well, if 1 over do is 0, if 1 over do is 0, remember, that means that 1 over di has to equal 1 over f. Right? So this point, this value here where it hits the axis, 1 over di, this value has to also be 1 over f. So we just got a measurement, or a calculation of the focal length. So if we can read this point off the graph, then we have the focal point. Okay? Now, we go the other way. What about at the top? Look at the top. It hits this axis. See, on this axis, go here, all the way down, all the way down, all the way down. When it's on that point, when it hits the vertical axis, that means the value of 1 over di, right? 1 over di is di. At that point, over here, 1 over di is equal to 0. And that means then that 1 over do has to be 1 over f, right? From the lens maker's equation. So on the top, if we can measure where the line, where this approximated straight line hits the axis, then this value should also be 1 over f, the focal length, okay? So the two intercepts where this line hits that axis, the vertical axis, and the horizontal axis, each of those points should be the value of 1 over f and 1 over f, okay? And so then we can get these values, take the average, and then take out percent error. Because remember, we took in the top, we measured the focal length by looking at where the lines from the lights above us were focused on a piece of paper. And we took the object distance, where the distance to the lights, about a meter, 1/100, was about 0. And so when we measured the image distance from our lens to the table where the lines were focused, that was our image distance. So that's our value for the focal length. And these values that we get from this graph, that's allegedly straight line, these values, this and this up here, 1/f, those values for f should agree with what we got by looking at the light and getting the focal length there. Okay, and then we can use our equation to get the percent error. If you remember, percent error is we take the absolute value, because percent error is never negative. X, whatever we're measuring, exact, with our best answer, minus X measured. Okay, take the absolute value, it doesn't matter, so it's always positive, divided by our exact result. And then to get a percentage, we multiply by 100%. Okay, so in this lab, you have to be good at fractions because of the lens maker's equations, and have some understanding of graphs. Okay, and what we did with this slide. Okay, in lab we'll explain it more, and also the Professor Gorbenko's videos on YouTube will hopefully explain this in more detail. Anyway, I hope this helped, and I hope you understand a little bit about this. Okay, take care.